This is the final review, exam 4, and we start with number 1 here, where we want to estimate the area with the left-hand sum, the right-hand sum, and the midpoint sum for this function f of x equals sine of x between 0 and pi, and in we're going to have 5 rectangles. And we're going to draw the picture for each sum and then use our calculator to actually find it. And so what you can do, if you like, we can get our calculator going, and I typically do on these types of problems. So here's my calculator, and I'm going to hit y equals and clear this out and plug in sine of x. So where's sine? There's sine of x. And then window, I'm going to go from 0 to pi, and then zoom fit it, and you're going to get a nice looking graph. And I can already tell you what it's going to look like, because I know what the graph of the sine function, what it actually looks like. So it looks like this. At 0, it's 0. And at pi, it's 0 again. And it goes up, hits 1 at pi over 2, and then comes back down right at pi. So this is my function f of x equal to sine of x. And I'm actually going to make this a little bit bigger, because I want to put an interval on there. Oops. Okay. So, and I want to do this between 0 and pi, and I want in 5 rectangles, so it's real simple. Let's mark off 5 little spots between 0 and pi. So length here is pi. To mark off 5 spots, to divide 0 up pi into 5 pieces, you divide by 5, so I'll have pi over 5. I'll have 2 pi over 5. I'll have 3 pi over 5. And then I'll have 4 pi over 5. And of course 5 pi over 5, which is pi. And I want to do these 3 different sums. I want to use the left-hand rule. So for the left-hand rule, let's put it in blue. I'm going to go from the left-hand side. So here's the left-hand side as height 0. And then up here, left-hand rule. Right, this is going to be the sine of pi over 5. Right, left-hand rule again. So up here, and then over and down. So this is going to be the sine of 2 pi over 5. Remember, left-hand rule, use the left-hand endpoint. And then this one's going to go up, go over, come down. So this is going to be the sine of 3 pi over 5. And I have one more to do. So it's going to go up here, over here, and down here. And so this is going to be the sine of 4 pi over 5. And all I need to do is compute these 5 areas. And so then I know if my integral is I, let's write down I is equal to the integral from 0 to pi sine of x dx. Then I know I is approximately, using left-hand rule, you simply calculate the areas of those rectangles and add them up. So the height is 0, whereas the width here is pi over 5. Plus the height is sine pi over 5. And I'll multiply by the width here, which again is pi over 5. And so maybe just to make this real clear, I'm multiplying this whole thing by pi over 5. Plus sine of 2 pi over 5 times pi over 5 plus sine of 3 pi over 5. You start to see a pattern emerging here, so you just start kind of copying it down. But realize what you're really doing, this sine of 3 pi over 5 times pi over 5 is really the area, again, of this rectangle. And there should be one more, so there's one more here, sine of 4 pi over 5. Of course, times then pi over 5. And so this is going to be equal to, so on my calculator, second quit, clear this out, and I can do sine of 0, which is height 0, but I can just put sine of 0, plus sine of second pi divided by 5, plus sine of second, oh, I should put 2 there, I guess, so 2 second pi divided by 5, plus sine of 3, oops, I don't need two parentheses there, sine of 3 second pi divided by 5, in parentheses, finally, one more, sine, left parentheses, oops, I always do that, 4 pi divided by 5, in parentheses, hit enter, and so that's when I add up all those signs, and then I'm going to multiply the whole thing by second pi divided by 5, and I'll round this to 2 decimal places, so this is approximately, oops, let's go right here. So this is equal to, let's say, 933, just 93. Let's do 1.93. Let's just do 2 decimal places. I can also do the right-hand rule, and let's do that one in red. Okay, so we did the left hand in blue. Let's do the right-hand sum in red. And if you do it in red, you start on the right endpoint and go over. So right endpoint, go over. Again, it's not perfectly drawn, just get the gist here, right? So over and then over like that. And so on this one, I can use these rectangles to figure out that I is approximately, and we'll compute the area of this one. And so that's sine of pi over 5 times pi over 5 plus then sine of 2 pi over 5 is the height of the next rectangle here, and then of course the width is pi over 5, so times pi over 5 plus sine of 3 pi over 5, times pi over 5. And here I'm not going to put the parentheses around the sign because you already know what I'm doing. So then plus sine of 4 pi over 5 times pi over 5. And there should be one more, and that's a 0. So I'm going to leave that alone. So this time plus 0, because the height of this rectangle is 0. I mean, you can take sine of pi, but sine of pi is 0. And I can use my calculator to crunch this thing. And so let's do that. And I'm actually going to pull up the previous entry. And the only thing I need to add in here is what? Do I need to add in anything in here? I have I have that rectangle, that rectangle, that rectangle. I don't think I really need anything to add in here. It should be actually exactly the same answer. I mean, you can, if you want, instead of writing sine of 0, you can delete this. And you have sine of pi over 5, sine of 2 pi over 5, sine of 3 pi over 5, sine of 4 pi over 5, and then plus sine of pi, which again is 0, so it's not going to change the answer at all, and then multiply again by second pi divided by 5, the width of each rectangle, and you get approximately 1.93. So they give you the same estimate. And then if you're going to use the midpoint rule, so here I'm going to have to do something different. So for the midpoint rule, let's look at this one. So I want to do the midpoint rule now. I got to first find the midpoint. And so it's really easy to find the midpoint. The length of this interval is pi over 5. This is going to be pi over 5 divided by 2. So it's pi over 10 plus another pi over 10 gives me the pi over 5 plus another pi over 10, so 3 pi over 5. This is 4 pi over 5. This must be 5 pi over 5. Oh, I'm sorry, this is 10, right? So pi over 10, 2 pi over 10, 3 pi over 10, 4 pi over 10, 5 pi over 10, 6 pi over 10, 7 pi over 10, 8 pi over 10, 9 pi over 10, 10 pi over 10, which is pi. And so you're going to plug in that height here and find this rectangle. You're going to plug in the midpoint to the function and find that rectangle right there. You'll plug in there and you'll find this rectangle right here. You'll plug in 7 pi over 10 and find this rectangle right here. And 9 pi over 10, you'll find that rectangle right there. And so this should be pretty easy. So I is going to be approximately, and you'll do sine of pi over 10. And of course, this will be times pi over 5, but I'll save that for the end. And then I'll have sine of 3 pi over 10 plus sine of 5 pi over 10 plus sine of 7 pi over 10 plus sine of 9 pi over 10. And this whole thing is going to be times pi over 5. And I'm just adding up the areas of these rectangles in green. So there's 1, 2, 3, 4, 5 different rectangles I'm adding up. And on my calculator, I can do this. So on my calculator, I have sine and pi divided by 10 and parenthesis plus. And then I have sine of 3 pi divided by 10 plus sine of 5 pi divided by 10 plus sine of 7 pi divided by 10, and then finally plus sine of 9 pi divided by 10. So if I hit all the correct buttons, this is what you'll get out, and then I'll multiply that by pi over 5 on the end. And so it's approximately 2.03, which is a little bit different from the ones before. And then I can use my calculator actually to figure out the exact answer. So what is I? Well, I can round it, right? So what is I equal to from 0 to pi of sine x dx? What is this actually equal to? So let's take a look. So go back to your graph, hit second trace, go down to number 7. Lower limit was 0, upper limit was pi. It's going to shade in the region for me and spit back the number of 2. Right, so the actual answer is 2. The important part of this problem, though, is to understand this idea. If you want to find the area or approximate the area, let's just use little rectangles. Now, there are some choices for the rectangles you could use. You could use the left-hand rectangle, which would start at the left endpoint over here. Or you could use the right endpoint, that's the right-hand sum. Or you could use a midpoint, which is the midpoint sum. Or you could pick some random point in between 0 and pi over 5. That would also work. And the more rectangles you take, the better approximation you get to the area. So remember, the actual definition of the definite integral, the integral from a to b of f of x dx, what does this definition look like? Well, it's simply, you have f of c sub I. If you want, you can write delta x, and you're just going to sum these areas up, right? This is the height of the rectangle, whereas this is the width of the rectangle. And we're going to sum these up. Maybe we go from I equals 1 to n. And so you have n rectangles, and the more you take, the better approximation to the area you get. As you let n go to infinity, you're going to get the actual area. So this is actually the definition of the definite integral. So hopefully you see all the different parts here. Now, of course, this underlining business isn't part of the definition. I just put it there, but there's a definition of the definite integral. The next problem we want to look at is we want to use our calculator to find the total area between the x-axis and the graph f of x equals x times x plus 3 times x minus 2 between negative 3 and 2. Okay, so what can we do? I guess I could just graph this thing. Since they tell me where to look, it's not terribly difficult to find the graph. So x, left parenthesis, x plus 3, in parenthesis, left parenthesis, x minus 2. My window, I'm going to go from negative 3 to 2, and I'll zoom fit it. And so here's the graph that I get. All right, so I can copy that down. So it looks something like, like this. Big, passing through 0, 0. Then small, like this. And this is negative 3. This is positive 2. And if you want to find this area in black, so A, it's going to equal to, well, you're going to have to split it into two areas, A1 and A2. So it's going to be equal to A1 plus A2. And the reason you have to do two different areas is because the definite integral is going to see this area down here and count it as negative. So what we'll do is we'll do two different integrals. So down here I'll hit equals. So maybe I'll just draw an arrow. Equals. This is going to be the integral from minus 3 to what? So minus 3 to 0. So minus 3 to 0 of my f of x dx. and then minus, because this area is going to be counted as negative by the definite integral, so the integral from 0 to 2, crosses through 0 there, of f of x dx. And so that's equal to, my calculator says, second, trace, let's integrate, so go down to number 7, from -3 to 0. It's going to shade in that region, and it's going to say it's equal to 15.75. And then minus, let's go from now, second, trace, to pull up the calculate menu, number 7, 0, enter, and then go to 2. And it's going to give me a -5.33333333. All right, so actually, I can make this, what, so -5.3333. This is probably repeating. And so this is going to be equal to then 15.75 minus, and let's just round this to 2 decimal places. Let's make it easy on ourselves. So 15.75 minus, I wonder if I do second answer, if it'll give me the right answer. And it will. Right, that answer that it's stored in there is actually the right one. But here I can do it. 15.75 minus a -5.33333, right? 21.08, let's say. So 21.08 units squared, if I round. Now what's interesting is that your calculator will store this number off your graph here. When I did this second trace, went down to number 7, I did the lower limit 0, upper limit 2. It actually stores that number in your last answer. So if I quit this mode and I do 15.75 minus my second answer, it's going to give me the exact answer. And I can even use the math button and go to fraction, and then it'll split out the fraction. So equal to 253 divided by 12. So if I need the exact answer, I know how to manipulate my calculator. I can find it. All right, let's take a look at the next one. And so on this one, we want to explain the significance of the fundamental theorem of calculus. All right, so this one's a little bit difficult. It's sort of open-ended. This is more, sort of set you up for some true or false maybe questions. But the idea is this: you have what's called a definite integral. And the definite integral looks something like this. These are the symbols we use, the integral from a to b of f of x dx. And when you see a definite integral, you should immediately just think area, because that's sort of what you're computing. So when I think of this, I think, oh, I'm trying to find the area underneath my function. So here's my function f of x from a to b. Now sometimes the definite integral will see this as being negative, typically when it falls below the x-axis. But in general, I think of this as being the area. And I gave you guys a definition above. Right? The definition for this thing was actually this is equal to the limit as n goes to infinity, the number of rectangles go to infinity. And this is the sum from I equals, let's say, 1 to n, f of c sub I delta x, where these are a bunch of rectangles. You can draw them. C sub i's are in some sort of little interval here, and then delta x is the length of the interval. You can draw these, little rectangles. And the more rectangles you take, the better approximation to the area you're going to get. Now the indefinite integral looks very similar to the definite integral, but of course they're very different. So the indefinite integral would look like something like this: the integral of f of x dx without limits of integrations. There are no numbers here, basically. And what this says is this is equal to the antiderivative. So antiderivative of f. So it's a completely different beast altogether. This one is area. This one is antiderivative. Now the fundamental theorem of calculus, the FTC, what it does is it connects these two. So it says if you give me a definite integral, basically, so the integral from a to b of f of x dx, and I want to figure out exactly what this definite integral is, what I can do is first figure out the indefinite integral. So take off the limits, and then put the limits back on. Right? Basically plug in the limits. So find first the indefinite integral, which is the antiderivative. And once you find the antiderivative, so suppose you found this to be equal to then f of x from a to b. And then this says you plug in b to the upper limit of the antiderivative, and then take off when you plug in a from the antiderivative into the antiderivative, where capital F prime of x is equal to little f of x. And let's do this backwards, right? So that is capital F is the antiderivative. And I'm actually going to go a little bit further. Is an antiderivative my spelling is terrible here, right? So anti is an antiderivative. There we go. So that's the significance of the fundamental theorem of calculus. In essence, if you want a short phrase, it connects the definite integral. It connects the definite and indefinite integral. Or even better yet, we can say it connects the area to the antiderivative. Any one of those I think is good for you to say. You know, if you just wrote down it connects the definite and indefinite integral, I think that's a good way to put it. It connects the area to the antiderivative, that's fine. You know, better yet, you know, saying all this stuff I said above is even better. You know, tell me what the definite integral is, tell me what the indefinite integral is, tell me what the FTC is. But really, I'm just looking for this idea that the fundamental theorem of calculus connects these two types of integrals, the definite and the indefinite, i.e., it's really connecting the area and the antiderivative to each other. All right, so moving on, some more sort of algorithmic or mechanical problems, some indefinite integrals. So we want to use the rules of integration to solve the following integrals. So let's just do these one at a time. So I want to do the integral of the fifth root of x dx. Now before I can integrate it, I have to write it as a power of x. So this is going to be the integral of x to the 1/5 dx. And this is simply a power rule for integration, so you add 1 to it. So 1/5 plus 1 divided by 1/5 plus 1, all plus c. And then 1/5 plus 1, well, that's 1/5 plus 5 over 5, so that's x to the 6/5 divided by 6/5 plus c. And that's equal to, when you divide by a fraction, you multiply by the reciprocal. So x to the 6/5 plus c. And because they gave it to me in radical form, I guess I should probably put it back in radical form. So this is going to be x to the 6 and take the fifth root. I can pull out one of the x's, and I simply get the fifth root of x, all plus c. And so that's my answer right there. Remember, you can check your work by actually taking the derivative. So I probably take the derivative of this part. So the 6/5 comes down, cancel the 5/6, take off 1, so x to the 1/5 plus 0. So it checks. The next one is the integral of x square root of x minus 1 over x dx. And here you have to be a little bit careful. This is equal to the integral. Now this is x to the 1, this is x to the 1/2. So exponents add, and 1 plus 1/2 is 3/2. So that's x to the 3 halves minus. Now you might be tempted to write 1 over x as x to the negative 1, which isn't completely wrong, but when you integrate that, hopefully you see when you add 1 to it, you're going to get 0, so you can't divide by 0. So you actually leave this as 1 over x because it's one of our types. And so down here, the first type, the integral of x to the 3 halves, that's a power rule. So you add 1 to it, so 3 halves plus 1 is actually 5 halves. And then divide by it. So divide by 5 halves. And then minus the integral of 1 over x is ln of absolute value of x plus c. And so this is equal to 2/5 x to the 5 halves minus ln of absolute value of x plus c. And because they gave it to me in radical form, I should probably put it back in radical form. So it's 2/5. Then x to the 5th, if you take the square root, you can pull out an x times x. You can pull out an x squared, square root of x, and then minus ln absolute value of x plus c. So that's my final answer. And part C, let's go back up and take a look at part C. All right, so here's part C right here. And so let's go down here and copy that one down. And so I'm just going to look off my review here. So I have the integral of cosine of x plus 1 over square root 1 minus x squared dx. And so that's equal to, now cosine of x, again, this is one of my types, so I'm going to guess it's sine x plus, and the integral of 1 over square root 1 minus x squared, again, that's one of my types, so that's going to be equal to sine inverse of x all plus c. And I can check my answer by taking the derivative. The derivative of sine of x is cosine of x, so that checks. And the derivative of sine inverse of x is 1 over square root of 1 minus x squared. So it checks. So that's good. All right, so moving on, if you look at D, E, and F, the next three problems basically, you'll see those are not one of your types, and so you're going to have to do something else to integrate them. So let's look at the first one. So the integral of 18x squared 6x cubed minus 7 to the 5th dx. And hopefully you realize it's not one of your types that you have memorized. So you have to turn it into one of your types by using U-substitution. So U is going to equal a thing on the inside, so 6x cubed minus 7. And then du is going to equal 18x squared dx. And the observation you want to make is that this is your u. So there's my u. And then my du is basically the stuff kind of left over. So here this 18x squared dx is exactly my du. And so this is going to equal the integral, and I have u to the 5th. So I have u to the 5th. And then that 18x squared dx is just equal to du. And so what you did is you took this sort of complex problem and transformed it into this sort of simpler problem using substitution. And you add 1, you can integrate a power of u. You add 1 to it and divide by it, plus c. And so this is equal to then left parenthesis, plug back in for u in terms of x. So 6x cubed minus 7 to the 6 divided by 6 and all plus c. And so that's my final answer for D. Part E is a little bit harder, but not much. And it's always good to kind of make a note and say what makes this problem harder. So I have 5x, square root of x squared minus 7, and all dx on the outside. So the first thing that makes this harder is this square root sign. So you really have to let it be the thing on the inside here. So x squared minus 7, then du is equal to 2x dx. And then you go to plug back in, and you can, again, if you get stuck, you just put a square or a rectangle here around u, so that's my u. And then my du, what I have left over is 5x dx. Now, I don't really care about the 5. All I care about is this dx, x dx. I need to get rid of that. Typically, the rule is if you're going to do substitution, you need to take out all the x stuff. You can't leave x and u's running around together, otherwise you'll get screwed up. All right, so you look over here and you say, well, I don't have x dx, I have 2x dx, but I can still circle x dx, and ask myself, how can I get that alone? And you just divide both sides by 2. So du divided by 2 is equal to x dx. And now we can plug in, this is the integral. I have a 5 here. X dx becomes my du divided by 2. And then you have a square root of u. So let's write u to the 1/2. And so this is equal to, there's a 5 on top, a 2 on bottom, the integral of u to the 1/2 du. And so I took this seemingly complicated problem right here and turned it into a nice easy problem right there. This is just a power rule. So I have 5 halves, u to the 1/2 plus 1, which is 3 halves, divided by 3 halves, plus c. And that's equal to, when you divide by a fraction, you multiply by its reciprocal. So you have 5 halves times 2 over 3, u to the 3 halves plus c. And so finally, this is equal to, the 2's are going to cancel right there. And I'm going to get 5/3. And because my problem was not given into u, it was given in terms of x's, I'll convert my u here back into x stuff. So u is x squared minus 7 to the 3 halves plus c. Now, I think this is a fine answer. It's nice to keep it actually this way. But if you really wanted to, since they gave it to us in radical form, you could write it as 5/3 x squared minus 7 times the square root of x squared minus 7, and then all plus c. But I think it's fine actually to leave it just like this over here. Okay, one more. So that was d, and so now this will be the last one, e. The integral of 1 over 5 minus 7x dx. Again, it's not one of my 4 types, so I'm going to let u be a thing in the inside. Well, that doesn't really work, but you only really have 2 choices, the top or the bottom for u. So let's let it be the bottom, 5 minus 7x. Then du will equal minus 7 dx. And you go to plug back in over here, and this is your u. And then you're just left with dx. So it's going to be the integral of 1 over u. And then you just have this dx, so you need to divide by this negative 7, so you get du divided by negative 7 equals dx. So this is du divided by negative 7. And so this is equal to negative 1/7, the integral of 1 over u du. And the integral of 1 over u du is one of my types. This is negative 1/7 ln absolute value of u all plus c. And that's my answer. And hopefully you can see this. I forgot to zoom in, but let's zoom out a little bit more so you can kind of see all these different ones we did. And I guess this one was actually part F, huh? So that was part F. So zoom out a little bit more. I want you to see it all right here. I want you to see first, how D, E, and F are all basically the same steps. Okay, recognize substitution and make your substitution. Right, make your substitution. Write them in the same spots each time. If you haven't been doing that all along, it's going to be hard for you to do it now, but start it now. Then you make your substitution. You make your substitution. You make your substitution. Then you integrate it out. So then I integrate this out. So there's my integral. All right, so down here, here's my integral. Right, down here, here's my integral. All right, and don't forget to put plus c. But basically, it's all the same stuff. And then you simplify if you need to simplify. All right, let's zoom back in. All right, so now we're back. And what we want to do is we want to find the exact area enclosed by y equals x cubed plus 1 and y equals x plus 1. So now if you're thinking you could use your calculator to do this, you can, but you have to be careful. You have to know where to look. So if you just try to put these in, typically I try to make the problem so you can't just figure it out. So if you're going to do zoom, I'd probably use standard window, so go down to Z standard. And you shouldn't be able to really see what's going on unless you know really where to look. All right, so you can see that they cross, but you're just not quite sure where they cross. So to figure out where they cross, it's when they have the same height. So what you would do is just take x cubed plus 1 and set it equal to x plus 1. And when you subtract 1s from both sides, they're going to cancel. And I'm going to subtract x from both sides, so I get x cubed minus x equals 0. I'll factor out an x, so x times x squared minus 1 is equal to 0. And then certainly I can factor this as x times x minus 1 times x plus 1 equals 0, which tells me exactly where to look. So if this a times b times c is 0, either a is 0, so the first thing is 0. The second thing is 0, so x is equal to 1. Or the third thing's equal to 0, x equal to negative 1. And these are my three sort of possibilities where these two functions are going to meet. So in my calculator, what I'm going to do is I'm going to go back to the window and go from negative 1 to 1 and zoom fit it. And that should give me a pretty decent window. All right, perfect. So what it looks just like this. From minus 1 to 1. And then here's this line. So you get two graphs. On top here, or this one right here, you have x cubed plus 1. That's y equals. And then this one right here, that's equal to y equals x plus 1. And you want to find this area. And so to find a, it's going to equal, and if you think about this, there's going to be two different things you have to find. This area here, so let's call that a1. Plus, let's do another area over here, a2. So you have to break it in two regions because the functions change which one is on top and which one's on bottom. So finally, this is equal to then, and for the blue one, we're going to do the integral from minus 1 to 0, because it's where they change, the functions change which one's on top and which one's on bottom. And so this one's on top at first, which is x cubed plus 1. So you have x cubed plus 1. And then minus the quantity x plus 1 dx. That one's on the bottom. Then plus, let's do the next one in red, the integral from 0 to 1. And now x plus 1 is on the bottom, and then minus x cubed plus 1 dx. If you can see that, that's a dx right there. And so that's equal to the integral from minus 1 to 0. And now on this, you have 1 minus 1. So minus, the 1's are going to cancel. And you get x cubed minus x dx. Plus the integral from 0 to 1. And again, 1's are going to cancel here and here. And you're going to get x minus x cubed dx. Which is equal to, and you simply add 1, so x to the 4th over 4 minus x squared over 2 from minus 1 to 0 plus x squared over 2 minus x to the 4th over 4 from 0 to 1. Which should be pretty easy to do. If you plug in 0, you're going to get out 0, so you're going to have 0 minus, and then you're going to have 1/4 minus 1/2. Plus, if you plug in 1, you're going to get 1/2 minus 1/4. And minus, if you plug in 0, you're going to get out 0. And so this is equal to a negative 1/4. A negative negatives plus 1/2. And plus another 1/2. And minus 1/4. And so what's that equal to? A 1/2 plus 1/2 is 1, minus 1/4, minus 1/4 is another 1/2. So that's equal to 1/2 units squared. And we can check our answer on this one. So if I want to check my answer, what's the easiest way to do this? So let's just do second, calculate number 7, and let's just do the first quadrant. So I'm going to go from 0 to 1, and it should go right underneath there. So I get 1.125. So I got 1.25 for that one. And then I'm going to do it underneath the other curve. So I'm going to hit down to go to x plus 1 and go from 0 to 1. And I'm going to subtract that off. So I'm going to get 1.5 minus, which is 0.25. They're symmetric, so I bet it's times 2, so I bet it's 0.5. I bet that checks. And so that's my answer. Oh, And so again, let's take a look at this problem so you can see it in full detail. First I figure out whether the heights are the same, then I can draw the picture from my calculator, and I realize there's two separate areas I need to compute because which function's on top changes at a certain point. So I do these two definite integrals, and I find the final answer. All right, so the last problem, what we want to do is we want to use the definite integral. We're going to use the fundamental theorem, of calculus to evaluate the following definite integrals and draw a picture of the shaded region you are calculating. All right, so part A, I want to integrate this from 0 to 4 of x root x dx. Oh, and there's a minus there, so x minus x root x. And I can draw this picture. I mean, it's really easy to do on my calculator. So if you have a calculator, let's do this. Make sure you do it with me. And so I have x minus x root x. And my window is going from 0 to 4. And I'm going to zoom fit it. And so I get something that looks just like that. So let's copy it down. It looks like the area is going to be certainly negative, so it goes from 0 to 4. And I'm computing the area of this region. And I can do this, again, on my calculator. I can figure it out. So second trace to put the calculate menu, number 7. 0, enter, 4, enter. And for my answer, I should get out approximately negative 4.8 about, right? So negative 4.7. Let's just copy that. 999. I bet you it's repeating. And so this is going to be equal to then, you add 1 to the exponent. This is just a basic one of my types. And then minus, I guess before I should do this, I should actually write this as a power of x. That might help. Equals the integral of x minus x times square root of x is x to the 3/2, because you have a 1 here and a 1/2 there, dx. Now I add 1 to it, so I get x squared over 2. And this is from 0 to 4 still. Minus x to the 3/2. If you add 1, you get 5/2. So divided by 5/2 from 0 to 4. And so that's equal to what? I have x squared over 2 minus 2/5 x to the 5/2 from 0 to 4, which again is equal to x squared over 2 minus 2. And x to the 5/2 is actually x squared, square root of x, divided by 5 from 0 to 4. And if you do that, I bet you can figure out this answer. So this is going to be equal to, what do I have? 4 squared over 2, so that's 8, minus, I have 4 times 4, which is 16, times square root of what? Square root of 4. Well, let's put it in there so I don't confuse anybody. That's divided by 5. And so that's going to be equal to 8 minus 16 times 2 is 32 times another 2 is 64 over 5, which equals, this is actually then 40 over 5 minus 64 over 5, which is a negative 24 over 5. And if you think about it, and it's negative, so important negative, not positive, but negative, because the area, most of this region falls below the x-axis, so the definite integrals don't count the area as negative. And if you think about it, 24 divided by 5 is what? 24 divided by 5 is 4.8, which is what that should probably have been. But you had to, you have some error when you approximate it, because the calculator is simply approximating this numerically. It's not actually integrating it with the fundamental theorem of calculus. Okay. Maybe you want to take a little bit of a break here and then come on back, but I'm going to keep on going. So part B, we have the, part B, I have the integral from 1 to e cubed of 3 over x minus 1 dx. Now you may not realize this, but I can integrate 3 over x. That's just equal to 3 ln absolute value of x minus the integral of 1 is x. And this goes from 1 to e cubed. And so this is equal to 3 ln, I don't need the absolute value because e cubed is positive, e cubed, minus an e cubed, minus the quantity, 3 ln of 1. I guess I put the absolute value on there, although I don't need to, minus 1. And so that's equal to, now 3, ln of e to the anything is the anything, so this is 3 times 3 minus e cubed, minus ln of 1 is 0, and so you get minus a minus 1, so that's a plus 1. And so my final answer on this one is equal to what? 10 minus e cubed. Let's draw the picture of this thing. So on my calculator, I can hit y equals 3 divided by x minus 1. So I'm just going to plug in the integrand. So minus 1. Delete everything else. Window 1, 2, e cubed. So second e to the 3. Then zoom fit. Let's see what I get. So I get a picture that looks something like this from 1 to e cubed. So I'm going to compute this area right here. And my calculator tells me that this area is going to be second trace, go down to number 7, go from 1, enter. And I bet you it says error. Let's see if it says error. Ah, it says error. It says error because when you go to it, hit go to, it'll say upper limit does not understand. That's because your window, when you set an e cubed, it set it as 20. So you need this to be a little bit bigger. So let's do 21. And now let's go to zoom fit. And you get basically the same looking graph because you just went a little bit further over to the right. And on this one, now you hit second trace, go down to number 7. Lower limit was 1. Upper limit was e cubed. And so there's my shaded region. And so this is about negative 10.08. And you can copy down the whole thing if you really want to, right? 5, 5, 4. And I can check it. On my calculator, I can take 10 minus e cubed, and I better get out the same answer, otherwise I made a mistake someplace. And I get out the same answer. So this checks out. This is good to go. Pushing along, we have part C. And part C is a little bit tricky. So I have the integral from 1 to pi over 2 of x squared minus 1 divided by x squared plus 1 dx. And if you think about this one, what you can do, and you really have to think here, so 1 over pi over 2. And the idea is really this. If you have 3 divided by 2 plus 2, in some sense, you could do, this is the same as 2 plus 1 divided by 3. So it's equal to basically 3 over 3 plus a 1 over 3. And then these cancel and you get a 1 here, so it's 1 1/3. And so you can do the same idea here. You say this is x squared, and you can add 1, and then say minus 2 there. That's minus 1, but you could write minus 2, because 1 minus 2 is still a minus 1. And then you have x squared plus 1 on the bottom, and then dx. Now what this is going to get you as a simplification, so this is the same as x squared plus 1. So you can pull apart the fraction, divided by x squared plus 1, minus 2 over x squared plus 1 dx. And so that's equal to the integral from 1 to pi over 2 of 1 minus 2 over x squared plus 1 dx. And I can integrate 1, the integral of 1 is x, minus 2 times, and the integral of 1 over x squared plus 1 is simply tan inverse of x. And I'm going from 1 to pi over 2. And so now I simply plug in, so I have pi over 2 minus 2 tan inverse of pi over 2 And then I'm going to take off when I plug in 1. So minus 1 minus, and then I have 2 tan inverse, and I'm running out of space here, 1. And so that's equal to, I have pi over 2 minus 2 and tan inverse of pi over 2. And then take away 1, and then take away, so take away, so a negative and negative, or minus and minus is a plus. And so then I have a plus 2 times, and then you have to figure out what the heck is tan inverse of negative 1, because it's of the tan inverse of 1, and that's actually equal to, if you think about it, it's equal to some angle. And so whenever I can't figure out tan inverse of a function, I say, okay, tan inverse of 1 is equal to some angle. Do I know, if you take the tan of both sides, so 1 is equal to tan of theta, and that means 1 is equal to the sine of theta over cosine of theta. So this basically says, do you know an angle when the sine and the cosine are the same? Because the sine of theta divided by the cosine of theta equals 1. You get the same thing. And that means theta must be equal to pi over 4. And so this is actually equal to 2 times pi over 4, which equals pi over 2. So what I'm going to get is I'm going to get pi, because pi over 2 plus pi over 2 is pi, minus 2 tan inverse. And you can't do anything with this one. This is pi over 2 minus 1. And that's my answer. Now again, you could actually, this one you could check your answer in the sense that if you didn't know what tan inverse of 1 was, if you do this, so let's see here, second tan inverse of 1, and enter, hopefully you can see, I don't know if you'd see that or not, that's pi over 4. I doubt you'd know that's pi over 4. It doesn't really jump out at me. So it's pi over 4. All right, well, that's the idea. Now, I can graph this. Oh, and I forgot to graph the other. So I can graph this one, right? So let's graph it and check our answer. So on here, I'm going to put left parenthesis, x raised to the 2 minus 1 in parenthesis, divided by left parenthesis, x raised to the 2 plus 1 in parenthesis. My window is going to go from 1 to pi. So 1 enter, second pi divided by 2. And then I'm going to zoom fit it. And I should get a pretty decent looking graph. All right, so there it is. So let's extend the page and draw the graph. So it looks just like this, from 1 to pi over 2. And it goes down here and goes up here. And we're trying to find this area. And my calculator says it's what? So let's see what the calculator says. Second trace. We can check our answer, see if we made a mistake. We went from 1 to pi divided by 2. And so this says this area is about 0.1338 2301. And so let's check it. What is this answer that I found? Well, I found this to be second pi minus 2. And I have second tan, to put the tan inverse function, of second pi divided by 2. And then minus 1. And hopefully, these answers are exactly the same, and they are. So that answer and that answer are basically the same. Three problems left. All right, no stopping us now. And so let's go down a little bit and do part D. Now, hopefully you notice that D, E, and F are not as simple as the ones before, really, because they're not one of our types. You're going to have to do a substitution. So we want to do the integral from 0 to 2 of x squared e to the minus x cubed dx. And I know these are not one of my types, so I know I need a u equal to, and hopefully you see the thing on the inside, which is this. So let's let u be equal to negative x cubed. And then the derivative of u with respect to x is minus 3x squared dx. And I'm even going to change my limits of integration. So since I was definite integral, this is the new part, right? So u of 2 is equal to negative 2 cubed, which is a negative 8. And u of 0 is equal to negative 0 cubed, which is negative 0, which is just 0. And so this is going to equal the integral from 0 to negative 8. Remember, the limits stay in order, so the 2 became a negative 8, so that's a negative 8 goes on top. The 0 stays 0, so that's still 0 on the bottom. And I have e to the u. The problem is, though, when I go to plug in for this x squared dx, I don't have x squared dx. I have negative 3 x squared dx, but this is my x squared dx, and it's easy enough to get it alone. All you have to do is divide both sides by negative 3. So du divided by negative 3 is equal to my x squared dx, and I got it. So that x squared dx gets substituted by du divided by negative 3. And so that's equal to negative 1/3 the integral from 0 to negative 8 of e to the u du, and that's one of my types. The integral of e to the u du is just e to the u. So I have negative 1/3 e to the u, and this goes from 0 to negative 8. And so that's equal to negative 1/3, and then e to the negative 8, minus a negative 1/3 e to the 0, which equals negative 1/3 e to the negative 8 plus 1/3. E to the 0 is 1. And so this is equal to, and let me clean that up because it's hard to see what I just wrote there. So plus 1/3. And so that's equal to 1/3 times 1 minus 1 over e to the 8. So that's probably how I would write my answer. And I can check my work by graphing my integral, my integrand. So here I have y equals clear. So I'm going to graph this right here. And then I can look for the area underneath the curve because that's what the definite integral says to do. So I have x raised to the 2, second ln to pull up the e to the negative x raised to the 3, in parentheses, window, we're just going from 0 to 2, zoom fit. And so here's the shaded region that I am computing. So I went from 0 to 2. It goes up, comes down. I'm trying to find this area, and I can do that. So hit second trace to pull up the calculate menu, number 7 for the integral. And lower limit was 0, upper limit was 2. It's going to shade in this region and spit back a number, which is 0.3332, and then 2151. And hopefully this number agrees with it. So let's take a look. My answer, which was right there, is 1 divided by 3, left parenthesis, 1 minus 1 divided by second e to the 8th, in parenthesis, and I get out the same answer. Right, so I'm going to check this one off. Looks good. Let's look now at part E. No, I mean part F, right? So I was A, B, C, D. No, this is E. So let's look at part E. That should have been, hopefully I wrote down D. Good, I wrote down D. So this is part E. And on part E, we have the integral from 2 to E, 3 divided by x ln of x quantity squared dx. And again, it's not one of my types, so I'm going to let u equal. And you only have one choice. You could let u equal x, but you get the same thing back. So I'll let u equal ln of x. And then du is equal to 1 over x dx. And I can change the limits of integration. So if you plug in e, so u of e is equal to ln of e, which is equal to 1. And u of 2 is equal to ln of 2, which equals ln of 2. And so this is equal to, and before I substitute back in, let me rewrite this. So 2 to e, and I can write this as, if you want, 1 over ln of x, quantity squared, times 1 over x dx. And I can pull that 3 out in front. And this integral sign, since it's dx, it's a net for everything that contains an x, but anything that doesn't have an x in it can go out in front. So you can't pull out ln x stuff out because it's a net for x, because you're a dx over here. But you can pull out a 3, because 3 doesn't have an x in it. But this makes everything real obvious if you think about it. So this is my u, so I'll plug that in for u. And then this is my du. That's my du. And so let's plug in. This is going to be equal to 3. I have new limits of integration, ln of 2. And the upper limit is 1. 1 over u squared du. So there's du, there's u. And before I can integrate this, this is 3, the integral of ln of 2 to 1. I have to write this as a power. This is u to the negative 2 du. So this is equal to 3 times, you add 1. So u negative 2, if you add 1, you get negative 1 divided by it from ln of 2 to 1, which equals minus 3 over u. U to the negative 1 means put it in the denominator, and negative is a negative sign, so negative 3 over, this is a u, not a 4, so u. And I'm going from ln of 2 to negative 1. Oh, not negative 1, to positive 1. See those negative signs? It's confusing me. All right, to 1. And so that's equal to negative 3 over 1 minus a negative 3 over ln of 2, which is equal to, you have negative 3, and minus a minus is a plus, 3 over ln of 2. And let's just keep it like this. This is fine. We can check our work. So to check our work, take out your calculator and hit y equals. And what we want to graph is the integrand here. So I'm going to graph 3 divided by left parenthesis x, left parenthesis ln of x, in parenthesis, raised to the 2, in parenthesis, and then window. I'm going to go from 2 to, so if I'm going to go from 2, instead of e, I'm going to put 3. Just like the last time we had that problem when we plugged in stuff with e, the window wasn't big enough. If you put 3, e's 2.718, 3 is bigger than e, so that'll be good. And then zoom fit it. And so that's what it looks like. And so I'm a little bit out of room over here, so I'm going to use this little space I have right here. Make a little box right here. I'm just use this little space. So what does it look like? It looks like this. I went from 2 to e. Starts up here, comes down here. I'm looking for this area in between, right there. And I can find it on my calculator by hitting second trace, going down to number 7. Lower limit was 2. Upper limit was e, so second ln. Put a 1 in there, so e to the 1. It's going to shade that region, and it's going to give me back this 1.328. So this is 1.3280. You can write down the whole number if you want. It's an approximation, so 0.851. And the area is approximately equal to that. And I'll check it. So I have negative 3 plus 3 divided by ln of 2 in parentheses, and I get back the same answer. So it checks. All right, so last problem, part C, or this is A, B, C, D, E, F. So part F, I have the integral from 0 to pi over 4 of sine of x over cosine of x dx. Now normally I see this integral written like this, the integral from 0 to pi over 4 tan of x dx, because that's the same thing, and it adds another level of complexity, but I didn't write it like that because I thought this way is actually hard enough. So we're doing U-substitution. You can let u be sine of x or cosine of x. If you let it be sine x, you're wrong. If you let it be cosine x, you're right. So u is equal to cosine of x. Du is then equal to negative sine x dx. Change your limits of integration. So u of pi over 4 is equal to cosine of pi over 4. And remember, cosine of pi over 4 is root 2 over 2. And then u of 0 is equal to cosine of 0, which equals 1. And so this integral is equal to, excuse me, it's equal to the integral from 1 to root 2 over 2. And hopefully you can see here that this is my u, And then sine x dx, that's going to be almost my du. I'm just off by that negative sign. So if you multiply both sides by -1, you're going to have it. So or divide both sides by -1, however you want to look at it. But if you multiply both sides by -1, you get equal to sine x dx. And then you just plug in negative du for that. So this is going to be 1 over u times negative du. I'll move the negative sign out in front. So -1 root 2 over 2. 1 over u du. That's one of my 4 types, so it's going to be negative ln, absolute value of u, from 1 to root 2 over 2. And that's equal to negative ln, and then you have root 2 over 2. You don't need the absolute value because root 2 over 2 is positive. And then minus a negative ln of 1. Again, you don't need absolute value on the 1 because 1 is positive, but that's 0. And so this is equal to negative ln of root 2 over 2. Now you may see this written like this, ln of 2 over root 2, because you can move the -1 here into the exponent, which means flip everything. And you may even see this written as ln of 2 of, actually, you may even actually see this written, if I was going to write this answer down as a multiple choice, what I probably would write this answer down as ln of root 2. Just like that. All right. Or I could even write this as ln of 2 divided by 2. That's also a good way to write it. How can I go from here to here? Well, if you think about 2 divided by root 2, you can multiply top and bottom by root 2, and you're going to get equal to what? 2 root 2 on top and a positive 2 on the bottom. And the positive 2's here will cancel. Those 2's will cancel and be left with root 2. So these are the same thing. So I guess most likely I'd probably just leave it like this. But this is a fine answer. I mean, you can leave it like this is a good answer. Just if it was multiple choice, it may be written in a number of different ways. Remember, it can be ln of 2 over 2 because you can write that square root as to the 1/2, and that 1/2 can come down in front then. And that completes the review. Good luck with the exam. Just joking again. Okay, so I want you guys to see the big picture. It's what I really want you to see. So let me go up here so you can see the big ideas. First, notice A, B, and C, they all basically look the same. So A, B, and C, the way they're done. And same thing with D, E, and F. So here's D and E. Let me zoom in a little bit. So on D and E, here they are. Notice the way we do these integrals by substitution. Here's my integral, here's my substitution, here's my change in limits. Here's my integral, here's my substitution, here's my change in limits. Make the change, okay, and then integrate, And notice I don't plug back in for x. You leave it in terms of u and use the numbers you found for u. If you convert it back to x, you're going to make this problem a lot harder than it needs to be. Same thing down here. Here's my integral. Here's my u substitution. Here's the change in limits. So I make my substitution, and then I integrate it out. Oh, we forgot to actually check this one. So let's check this one. And so on this one, I have sine of x divided by cosine of x. And my window is going from, 0 to pi over 4. So 0 second pi divided by 4. And then zoom fit it. So I should draw this then. Down here, I should draw the graph. So my graph looked like from 0 to pi over 4. And what did it do? It just went up, didn't it? So it just goes up. And so I'm looking for this area. To find this area, hopefully it's ln of root 2, so let's check it out. Second trace, number 7. I'm going from 0 to pi over 4. Shades in that region and spits back a number, which is 0.346. 46 5, 7, 3, and then there's 2 more there, 5 and 9. And I can check it. So second quit, ln, second root 2. Right there. And you get back the same answer, so it checks. Good. Now I'm done.